Hi everybody, welcome to virtual PyCon. Really excited to be able to give this talk today. It's about why is Python slow. It's quite a controversial topic, but hopefully we're going to get stuck into some facts here and focus solely on, engineering and science rather than opinions. So we're going to be digging into a bit more about like the Python compiler and where potentially there could be performance improvements in the future. Secondly, I just want to say thank you for joining. I hope everyone is safe at home, and thank you so much as well to the PyCon organisers for being able to pivot around this crazy situation that's been happening so far in 2020. Hopefully you enjoy this, and let's get into it. So if I say Python is slow, it has to be compared to something. And to be more specific, when I talk about Python, I'm referring to CPython. So that's the version of Python you download at python.org, the one that comes bundled with macOS, and the one that's on the Windows Store. So if we take a look at a CPU intensive benchmark, this is the famous N-body program, which models the orbits of Jupiter, Saturn, Uranus, and Neptune, a task that we do on a regular basis. So the C in CPython is named after the language that it's written in. CPython is a Python interpreter written and compiled in C, but if you compare the execution time of the same algorithm in C, it's 7 seconds versus 14 minutes. It's not even on the same planet in terms of performance. So C and CPython aren't really a great comparison. This is really apples and oranges. C is a strongly typed compiled language, and Python is a dynamically typed interpreted language. But what about Node.js? Node.js sits on top of the Google V8 JavaScript engine. It's actually a better comparison because it's also dynamically typed and it's interpreted as well. So what does Node have that makes it so much faster than Python when it comes to calculating the orbits of planets? So before I go into that, let's just recap how CPython actually runs code. So Python code is portable. You can download Python source files and they'll run on Windows, Linux, macOS. When code is actually read, it's parsed into an abstract syntax tree. This is a representation of what makes Python Python. It's a tree that represents functions, statements, operations, everything you'd expect to see in a Python application. So after completing the task of parsing, the interpreter has an AST with the operations, functions, classes, and namespaces of the Python code. The job of the compiler, though, is to turn the AST into instructions that the CPU can actually understand. You can't give the CPU an AST to execute. The CPU really only understands like small instructions, small operations. It's essentially just a really powerful calculator. The compilation task actually is split into two parts. There's the compiler, which traverses the AST because it's a tree, and it creates something called a control flow graph, or a CFG. The control flow graph basically represents like the logical sequence for how the code will actually run, not what the code is. Then there's the assembler, which basically goes through the control flow graph and then turns that into sequential statements, which are known as bytecode. This bytecode is really the atomic level of a Python application. It doesn't really go any smaller than that. In an evaluation loop, each of the bytecode instructions is taken and executed using something called a stack frame based system. Stack frames are a data type used by many runtimes, not just Python, but stack frames allow functions to be called and variables to be returned between functions. So stack frames contain things like arguments, local variables, and other stateful information, as well as the code to be executed, and the environment in which they live in, and also the thread in which they're supposed to run on. So a stack frame exists for every function call, and they are stacked. That's why they're called that. They're stacked in sequence in the terms of which order they were called in. You'll see a frame stack actually anytime you have an unhandled exception and it prints a stack trace. That's why it's called a stack trace. It traces up through the stack and tells you what frames are being executed when the error occurred. So reading, parsing, and compiling Python code is time consuming. It's a lot of work. It puts pressure on the CPU. So that compiled code is actually cached anyway. And this is what lives inside your dunder PyCache folder. And each time you run the code again, if the code hadn't changed, then the cache version is read and read using the Marshall module. any optimizations above the line, so in terms of like reading, parsing, stuff like that, wouldn't make any difference to the benchmark because it's not actually going to impact how fast the code actually executes, because the CPython compiler is what's called an ahead of time or AOT compiler. So it's all compiled up front. When CPython executes compiled code, it uses like a central frame evaluation loop. It's in a file called ceval.c if you want to go and have a look at it. Takes a while to get your head around, but this loop is basically just a big for loop that goes through all the bytecode instructions, and it's got inside it a massive switch statement, and it says if it's this bytecode, do that. If it's that bytecode, do this. And it takes values from the value stack, which are typically variables, or they could be other things. It goes through each operation inside the loop, and it evaluates it. But because so much of CPython is based on top of compiled C code, a lot of the bytecode operations are in fact just calling compiled C functions. So why is compiled C code so much faster than CPython, which is just running compiled C code? Well, I think the clue is kind of in that loop. So each cycle of that loop is not free. It's actually machine operations that need to go through for each bytecode operation. And the shorter the task, the shorter the time it takes to actually run the bytecode operation, and the more loops there are, the more significant that overhead becomes when you look at the time. Or actually, when you look at the benchmark, that's pretty important. So when you compare the n-body benchmark with C against CPython, it's absolutely slower because this benchmark uses really tight loops. It uses lots of really small arithmetic operations. They're not complicated operations. This is like add this number to this number, but do it like millions of times. So the CPython interpreter is basically just going around in a loop again and again and again, and it spent a lot of time just going around in the loop to get to the next bytecode. So if CPython could know that it's going to execute a tight loop, surely it could plug in some shortcuts or something, like it's kind of like short wire the loop. To understand that, we really need to actually look at the compiler and how the compiler works. So there are two types of compilers. There's an ahead of time compiler like CPython, or there's a just-in-time compiler, or a JIT. JIT compilers are very different because they compile just in time. They don't parse the code just in time. They parse the code ahead of time, typically, and then they use some kind of intermediate representation between the parser and the compiler. So this is a lower level. This isn't an abstract syntax tree. This is a lower level than that. And that happens at the pre-compiler stage, basically. It's not as concrete as a compiled code object like Python, but it's a lot lower level than an abstract syntax tree. So one of the big benefits to a JIT compiler is that it's really good at solving the tight loop problem. PyPy is a good example. PyPy is an alternative Python interpreter. You can use it to execute your existing Python code. It's open source and it understands Python 3.6 syntax. Also, unlike CPython, PyPy is written in Python. So the CPython compiler is written in C, the PyPy compiler is written in Python. Actually, the whole of PyPy is written in Python. So if my leading statement were true and Python is slow, then a Python compiler and interpreter written in Python must be like ridiculously slow, right? Well, actually, no, it's not. For the n-body algorithm, PyPy is actually 650% faster than CPython. So I'll just take a pause for that to sink in. There's a few reasons for this, but they all relate to optimizations. The problem we were looking at was the tight loop problem. And because PyPy uses a JIT, it's able to basically assess the algorithm and the data flow and make decisions about how it should be executed. It can change the execution structure just in time rather than having that all determined up front. The execution structure is optimized to the problem set that it's been given. So JITs are really effective at repetition and loops. So if they can assess the problem set and say, this is a lot of repetition here, these are known as hotspots. And what JIT compilers can do is they can say that piece of code is going to run a lot, so I'm going to make that really efficient. And it does have an overhead, which we'll talk about. But JIT compilers can change the way the code is compiled and they can inline statements, so basically squash them together. So rather than going around the loop, actually stack everything in a sequence. You can imagine with CPython, if it had that feature, like how much faster it would be at that particular problem. PyPy isn't the only Python JIT out there, actually. Number is another JIT compiler specifically targeted actually for NumPy usage. You can use Number by importing a JIT decorator and wrapping just a function with that decorator. If you're doing tight loops or any kind of repetitive number crunching, Number is actually a really great alternative to CPython. Actually, you use it with CPython, so it's more that you wrap the JIT and pick particular parts of your problem set that could be optimized using Number's JIT, especially if you're using a lot of NumPy. So this isn't the only alternative when it comes to removing the overhead of the evaluation loop. When CPython runs functions that are in compiled C extensions, so that's one of the big benefits of CPython, is that it works really nicely with compiled C code. The bytecode is a single operation. So if you want to call a C function, that is a single bytecode. All of the tight loop can happen on the right in this diagram over in a compiled C binary, but this doesn't really answer the original question of why Python is slow. It's actually just saying if we just move it all to a compiled C function, then Python is faster, but you've basically solved the problem by using C and not Python. So if JITs are really fast, then do all of the compilers on the benchmark that we showed earlier, they must all have a JIT, right? Well, again, no. So there's AOT compilers, so Rust, C, C++, but these are all strongly typed languages and they will have static memory allocation or dynamic or automatic. They work very differently into the way that Python or even Node or Java or C# allocate memory and work with objects. So it's really chalk and cheese to compare Rust or C or C++ with Python. A fairer comparison actually is Node.js. So Node.js is the server-side JavaScript runtime, but on the Chromium V8 engine. The Chromium V8 engine is the JavaScript engine that sits in the Chrome browser, and it's also used to power a number of other things, including Electron.js apps, which you've probably got on your desktop. I mean, Slack is one good example of that. But you can see that on the benchmark, Node's actually massively faster than Python. So JavaScript has more similarities to Python in terms of its language and dynamic typing, for example. But earlier I mentioned how JIT compilers use an intermediate representation. So CPython also has an intermediate representation, which is a graph of basic frame blocks. So when your Python code is compiled, the execution sequence is determined and the compiler emits frame blocks in a control flow graph, which I talked about before. So if you take a simple for loop, that actually has many parts, so it actually ends up as many frame blocks, not just the one for the entire for loop statement, because inside the loop you could have a block which could call some other code which could then call another frame. Also you can have else statements in for loops, which I never quite understood why, but you can do it. So a control flow graph actually for a for loop could be quite complicated, but it's rigid. It says this is how the code will execute. All of this is sent to the assembler and then it spits out the sequential bytecode. If you contrast that to a JIT, which compiles later on, then some intermediate representations that JITs use are actually a lot more flexible in terms of the execution path. So the code will run the way you expect it to run. That's not the point. It doesn't surprisingly go off on a different branch. It's more about how the compiler actually looks at the blocks of code or the statements or the operations and also the values that make up the code and how it decides to actually send those to the CPU to be executed. This is really about making sure the CPU is being used in the most efficient way possible. So one intermediate representation property is called static single assignment. So if you look at V8's JIT optimizer, so this is the optimizing compiler for V8. It's called Turbofan. It does some really cool things with static single assignment intermediate representation. So all values and operations. So in a Python equivalent, that would be all variables and all operations, all parts of a statement. All of those things become nodes in this massive graph. Python's kind of got a similar thing with AST, but when it actually comes to executing, it's all in sequential bytecode. Whereas if you compare that to Node, basically all that stuff becomes nodes, oddly enough, in a massive graph. And the graph isn't determined in terms of like, here are all the edges on the graph and here's how it should execute. The graph is actually determined in terms of dependencies and data flow. So the compiler's optimizer actually makes decisions about hot code and dead code, and it draws edges in the graph to optimize the way that the code is executed. So by finding dead code and making sure that that doesn't get scheduled, or finding hot code and making sure that that gets scheduled properly, you can make some massive efficiency gains. So that's one of the reasons why in that benchmark, Node was so much faster, even though it's dynamic, is because its JIT compiler is able to be really smart about the way that it basically optimizes certain parts of your application. So V8 isn't the only JIT to use SSA. Most modern JITs use SSA as well, including PyPy, and Numbers JIT also uses a SSA representation. So if JITs are so great, why can't CPython have a JIT? I've kind of mentioned the clue a few times. CPython and C extensions go hand in hand. Half of CPython is in Python and the other half is in compiled C code. Compiled C code cannot be JITted. It is rock solid. It's not going anywhere. For a JIT to be effective, the JIT compiler needs to be able to make assertions about the code structure and the data flow and the way that it's being executed. But from Python's perspective, the compiled C modules then become a black box. Like, you don't actually know what's in them, and you can't see the control flow inside those compiled modules. So the JIT could really only work on the Python side, and then you'd kind of have to stick a JIT with AOT compiled C code, and you're not going to get anywhere near the efficiency gains that you would have in just like a pure JIT compiler. So this, I guess, is one of the reasons why CPython can't have a JIT compiler. Something else about JITs that I haven't mentioned is that they have an overhead. So, all this clever optimization like has a cost. Firstly, they have a memory overhead. I don't know if you've noticed, but Node uses quite a lot of RAM. That's not the only reason why, but the JIT is quite a complex piece of software and it doesn't come for free. Second, they have a startup overhead. So for a JIT to basically get running, it has a startup time. So if you stuck a JIT in CPython would take longer to start. Now, that might not sound like a problem for most people who just type Python at the command line and the REPL comes up, quickly. The CPython compiler as well was never designed to be optimized for a particular problem set. It's supposed to be general purpose. And the compiler, and it says in the design notes of the compiler, is supposed to be simple. So introducing a JIT would really go against the design principles. And sure, you could optimize a particular problem set like the tight loop problem that we discussed, but there are actually other ways you can solve that problem anyway that exist at the moment. So it's not to say that CPython doesn't have any optimizations, because it does. It has something called PGO, or profile guided optimizations. The CPython source code is compiled to make a binary, and then that binary is then given. So Python is basically run with a test application. The test application is actually the part of the unit test program, but under test, the application is profiled, and then it's seeing which parts of the Python binary are used the most. This spits out something called a profile, and it identifies what hotspots there are on the app. Those hotspots are then basically like optimized just in the same way that a JIT would, but that's done once. So that's done before the version of Python is built for you all to download. One person does that. So the release manager probably runs the PGO process, and the profile is basically like hard coded into the CPython binary. If you want to run your own profile, you can download the source code and run your own profile. But you're probably going to come up with a similar answer, which is that there are parts of the CPython binary which are run a lot, and those include things like dictionary key lookups, hashing algorithms, stuff like that. There's small functions which are run a lot in the lifetime of CPython, and those are already optimized. So to recap on what almost turned into a talk on JITs, is A JIT can optimize at runtime. An AOT can't make those kind of distinctions. JITs are great for repetitive math-heavy tasks, but for unpredictable tasks, they're not so great, which we'll talk about. If you have those types of problems, then you should use Number or PyPy, and you get a JIT for free, and you get all those big performance boosts. But like I said before, JITs are not free. I say free in terms of cost, but not free in terms of CPU. We were comparing the speed, purely the speed of Node and CPython for the n-body problem. But actually, if you go and look at the benchmark, Node did actually finish that task, great, but it used over 4 times more memory. So if the Achilles heel of CPython is these small tight loops, then what about other types of tasks? Like which types of tasks is it good at? Like which ones is it efficient at? One of those tasks is text processing. So another benchmark is basically doing regular expressions over random DNA strings. CPython is significantly faster than Node.js and is actually in the same league as some statically typed algorithms. So it's not all bad news, and there are applications where CPython's compiler design is actually quite efficient. But this is all about slowness, and it's not just about compilers. So are there any other optimizations that CPython could have? What about memory allocation? So not just on the amount of memory, but also how CPU is used, allocating and deallocating memory. So whenever you create objects and you destroy objects, which actually happens a lot in the life cycle of an app, thousands and thousands of times, objects come and go as you bring functions in and out of scope, for example. So how efficient is CPython at actually doing that? Because that adds both memory and CPU hit. A good benchmark to look at would be the binary tree benchmark. This particular benchmark basically constructs, traverses, and destroys binary trees again and again and again. It's a good benchmark to use for memory allocation overheads because it indicates a lot about the garbage collection algorithm, and it also looks at if it uses a GC, and it also looks at the cost of memory allocation. So creating all the nodes in those binary trees essentially is allocating memory and deallocating memory. So because Node has a similar memory management story to Python, I'm going to pick on Node again. CPython has 2 strategies for making sure your apps don't eat all your RAM. The first one is simple. Everyone should understand this. It's everything in Python is an object, right? So every object has a reference count. If that count ever goes to 0, the object is destroyed and the memory is freed. But if you have container types like lists, dictionaries, sets, for example, they can reference themselves, which you might think this is a slightly contrived example, but it actually happens a lot more than you'd think. Even just starting Python, this happens. I think I tested it. It was like thousands of times it creates cyclical references. So if you just relied on a reference counter, the memory would balloon and the process would blow up. So another tool is used called garbage collection, which basically looks at cyclical references and then reduces those down so the object can be freed. CPython has a stop everything garbage collector. So after a certain number of cycles, it will ask every container object to check itself for cyclical references. So it will go and find every dictionary, every list that's been allocated in the whole application space, and it will go and ask it to check to see if it has any cyclical references. So that's only done every now and again. It's only done every certain number of cycles because it's quite costly to the CPU. It then goes and marks the ones that are required for removal. So if it has cyclical references and it reduced that number and it gets to 0, that object is actually never referenced by anyone, so it can be freed. This happens on the main thread. So whilst all this is happening, whilst every dictionary is being checked, every list is being checked, nothing else is running. No other operations are running on that CPython process. So if you compare that, for example, to the V8 engine, which follows a similar strategy, it has a stop everything garbage collector, but it actually uses a slightly different technique to make that faster. Because it's stop everything, the time taken to stop, you want it to be as small as possible. So the traversal and the marking of objects, it's actually done on 2 helper threads. So it's done basically in parallel, before the main thread is paused, it means a lot of the sweeping process is done in a shorter period of time, and the main thread is only paused for a fraction of the amount of time it would be otherwise. So it might sound like a small difference, and it is milliseconds, but in certain benchmarks and definitely a lot of applications, if you're hitting the GC a lot because you're allocating and deallocating objects, then this kind of optimization is going to make a pretty good speed improvement. So on that particular benchmark, it's going to become really obvious because this binary tree problem is basically going to hit the GC thousands of times. So it sounds like a fancy feature. So why can't CPython have one of those? So to take a quick pause, the Chromium engine is developed and owned by one of the biggest companies in the world. It's the company that makes billions of dollars in profits. And the Chromium project, like I was looking at on GitHub, and I can see at least 30 people who are working on it full-time, 5 days a week, and they are all very experienced developers. So even if you were just to work out like the cost of running a team, 30, maybe it's probably more, 30, 50 developers running on that, I don't think that's actually a fair comparison. CPython is a community-run project. It's developed by volunteers. All of the people who write and work on the CPython compiler have day jobs. So I actually feel mean comparing Node.js to CPython, because I know the people who work on CPython, and like they're all super smart people, but they're volunteering and they're doing this in their spare time. So to say, look at all these shiny features you can get if you've got $10 million a year to spend on development, that's great, but like as a project we don't have that. So sure, the GC could be multi-threaded, I mean technically it's possible, and I don't think it has anything to do with the guild. That's not the reason why it hasn't been done already. It's just about who's going to do it, who's got the time, and who's got the experience. So that's my pause. I just want to say that because I know that some of the people watching this show, some of the people watching this video, will be on the dev team, and it feels like I'm just attacking the project, which I'm really not. So on the topic of the GIL, is that actually what's killing performance? This is not a GIL talk. So for CPU intensive tasks, if you want to run them in parallel, then there are solutions to do that in CPython today that get around the GIL. So multiprocessing, the multiprocessing package is a great solution. All you need to do is figure out how do you split your workload up into big enough chunks that the overhead of starting a new process doesn't become impactful in the execution time. Alternatively, Number can do a no-GIL JIT, which is pretty nice. Multiprocessing, like I mentioned, does have an overhead, not just in starting a separate process, but actually like the overhead of running the process. But it doesn't really matter as much, because if you're saying parallel, then how many CPUs and how many cores do you have? If you're talking 4 or 8, then running 8 Python processes is not a significant overhead. If this is not that type of problem, then async IO and multi-threading are actually a better solution. So in this benchmark, this is actually one that I wrote. This is a TCP port scanner used for testing purposes, which I just wanted to see, like if you wanted to run a task concurrently, like checking 20 TCP ports, each with a timeout of 1 second, then how close does each approach get to 1 second? Because the minimum is 1 second, because if one of the ports is closed, then it's going to time out after a second. But how close does it get to that? So async IO is the fastest, because this is a IO problem. This isn't a CPU problem, so the GIL's got nothing to do with it. In this particular benchmark, async IO is actually the best approach because it's got the smallest amount of overhead in terms of running concurrent tasks. But sometimes you've got a problem which is both IO bound and CPU bound. So in those cases, the new solution, which is going to be coming in 3.9, is subinterpreters, which is going to be the new hotness, and I'm super excited about it. But it's still experimental, and basically it gives you the ability to run multiple interpreters rather than multiple processes, and interpreters have a much smaller footprint. Also, it's a bit easier to share memory and stuff between interpreters, but definitely not as easy as async IO. So if you have a problem that's CPU bound and IO bound, then this potentially is a great alternative. So in summary, modern speed with modern compilers is about optimizations. Tight loops, like the tight loop problem, really hurts CPython. Its compiler is not designed for that problem. And if you look at those benchmarks, it's going to look awful. But not all problems are a tight loop problem. If you do have that problem, other implementations are available. Parallelism improvements are coming in 3.9 and 3.10 in the form of sub-interpreters, and there's still quite a lot of work to be done there. If you do want to chip in and help out with that work, that would be awesome. I think the GC potentially could be optimized and improved, but I wouldn't expect to see like a massive improvement for just general problems, the general applications. In some problem spaces, the GC optimizations could actually make a pretty decent difference. But lastly, optimizations cost money and they cost time and they cost effort and they cost planning. These are complex things. This is not a simple thing that we can just go and hack in a few lines of code. And CPython is general purpose. So if we make optimizations come with compromises. And there are optimizations available. There are other approaches to Python. So my leading question, is Python slow? Well, actually, the answer is you can pick different interpreters. And the interpreters have been designed to different problem spaces. And each of those interpreters have been optimized to different problem spaces and actually are very fast. So if you pick the one which is general purpose and you apply it to a problem space which it wasn't designed for, if you measure a fish by its ability to climb a tree, you're not going to get the best outcomes. So finally, I hope you enjoyed my talk. It's been really fun to give this talk, to do the planning. Also, I am working on, finished now, a book on CPython internals, which I'm publishing with the Real Python crew. This is going to be out as a physical book in a month or so. If PyCon was going to be on face-to-face, we were actually going to have a pile of books at PyCon, so it's a real shame. But basically, I dig into the compiler, actually just pretty much everything that's in CPython in the source code. Anyway, it's a real technical deep dive. Check out my website. If you have any questions, email me, or you can find me on Twitter at the usual address. So thank you very much. And again, thank you to the PyCon team and the PyCon committee for making this happen. And please donate to the PSF. Goodbye.